Hello viewer, the topic of this group project is Neural Radiance Field based 3D scene reconstruction of a desert environment. The main problem statement is to apply NeRF technique to reconstruct a real desert environment in a virtual three-dimensional space with the help of multiple 2D images taken at various angles from the landscape. The motivation behind this project is to ultimately build a robust system which can be deployed to achieve strategic advancement in desert surveillance and warfare. By deploying a sophisticated 3D scene reconstruction system on tanks, the project aims to minimize human risk during military maneuvers while significantly enhancing the coverage and accuracy of surveillance in challenging desert terrains. Beyond the immediate defense applications, the system's ability to identify potential threats, camouflage, and evasive tactics contribute to advanced threat assessment and strategic planning. NeRF is a technique that uses neural networks to model the volumetric representation of a 3D scene. It operates by learning a continuous function that maps 3D coordinates to radiance values, which represent the color and transparency of the scene. NeRF is employed for reconstructing 3D scenes in highly detailed and realistic manner. Unlike traditional methods that use explicit geometric representations such as meshes or point clouds, NeRF uses implicit representations, enabling it to capture complex scene, intricate details, and variations in lighting conditions even for challenging landscapes such as deserts. The process of 3D scene reconstruction involves transforming real-world data obtained from sensors or cameras or imaging devices into a digital representation of a 3D environment. This includes capturing the geometry, spatial relationships, and appearance of the objects within the scene. For this project, a set of 2D images of desert are used to reconstruct a real-world scene in 3D environment. NeRF optimizes a volumetric representation of a scene as a vector-valued function, which is defined for any continuous 5D coordinate consisting of location and view direction. The scene representation is parameterized as a fully connected deep network that takes each single 5D coordinate as input and outputs the corresponding volume density and view-dependent immediate RGB radiance at that location. It then uses volume rendering techniques to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we are able to optimize this scene representation by minimizing the error of rendering all camera rays from the collection of RGB images. As discussed earlier, to reconstruct a 3D scene, we require a set of 2D images. In this project, we used both real and synthetic datasets. A desert environment was built in Unity simulation software. A robot with a camera mounted on top was controlled through robot operating system. The robot was traversed the entire desert field and captured image data from multiple angles. For the real dataset, we used a nearby sandy terrain to collect images. The camera position and angles of the images were later extracted using Colmap. We shall now look into the results of this project. First, we tested our model on simulated dataset. The robot was operated on a straight trajectory, which is closer to a real-time application. We then did an ablation study to understand how the results would vary over a circular trajectory. In this simulated run, we observed that all the camera poses are at a uniform height from the ground and are evenly spaced out. This was achieved with the help of ROS, which enables the robot to work in a very controlled manner, and the user has all access over the trajectories of the robot. We shall now look at the results of 3D scene reconstruction of a real desert environment. We can see that there are more features and textures in this environment as compared to the simulated one. However, since the images were captured by human hand, there is a non-uniformity in the camera pose for every image, and it can be seen in the white voxels, which represent how the camera poses extracted by Colmap are not that uniform as compared to the simulated one. However, with fine-tuning the model parameters, we were successful in obtaining a satisfactory result of the 3D scene reconstruction. The primary challenges faced during the course of project were mainly that of acquiring data. Since there is not much real desert dataset available, we had to rely on simulated and make-do dataset. The second major challenge we faced was extracting camera pose for each image from the given image dataset. Colmap was used for this, but the homogeneous nature of desert dataset didn't offer many features for the differentiation between frames. This was observed as out of 82 images given as input, Colmap could extract differentiable features for only 35. Coming to the future perspective of this project, it is an exciting field as the task of building a robust system that can be deployed on a tank will extend the model project into a real-time system. The group would like to thank Dr. Anand Mishra, instructor of the Fundamentals of Machine Learning course, for giving us this exciting opportunity. Thank you.